good to see you guys back here. Excuse me for the noise. My wife is helping me with some dinner. Um, so the discussion of today will be the part two of our Mueller effect. So let's quickly get to this.
So we can pat ourselves on the back since we have done all of the prep work for in the previous part of Mueller effect. Now we can go directly and see what is the Mueller effect. So what is Mueller effect? Mueller effect is basically a multiplication effect of C mu in the circuit application. What is C mu again? C mu is basically the internal capacitance between the base and the collector. So if I, as you can see here, if I have this amplifier circuit, and you can see that the ground is on the emitter side of this circuit. Therefore, this is a common emitter circuit with signal current source at the input. Okay, so as input of this circuit is in the form of current, we can consider the output in the form of current by measuring the output voltage across a load resistance. So now we can convert the original circuit to its equivalent hybrid pi model here. So keep in mind that this particular model here, we assume that the frequency is sufficiently high for coupling. Coupling is this, and bypass is this. So the coupling and bypass capacitor will be short circuit because frequency is high enough. Plus, we have to assume there's no early effect. Therefore, the RO internal resistance between collector and emitter region, C prime and E prime, will be open circuit. Up to now, without taking the effect of C mu into account, the signal is usually cascade from the input to the output, and there is no connection between the input part and the output part, right? But now by taking C mu into account, now C mu will become a feedback element that connects the output back to the input. In other words, the output now can actually influence your input. So if you can see in here, how does that happen? So if you change your output voltage in a certain way, you can actually charge your CMU capacitor, right? When the CMU capacitor now can actually store charge and discharge back to the input, and they can influence the V pi voltage. So that's how you have the output influence back the input in this case. So as you can see in here, adding C mu in the circuit make it a little bit more complicated to analyze. Therefore, in order to easily analyze this section, we can take just this particular section out and treat it as a two-port network, like in this figure here. So if you take this section out and treat this as a two-port network, we can have the input of the network will be V pi for the voltage, and the output can be VO. Likewise, the input and output current can be I1 and I2 respectively. So if you apply KVL, Kirchhoff voltage law, from the input and clockwise, you can write an equation to relate. You can have an equation of V pi, which is this, equal to the voltage across this impedance or this capacitors. So I1 multiplied by impedance of C mu plus output voltage VO. So you can write the impedance of C mu as 1 over j omega C mu. Now you do the same thing, but from the output counterclockwise, you can have VO equal I2. I2 across the input, the impedance of C mu is I2 multiplied by 1 over j omega C mu and plus V pi. Now we have an equation for V pi and equation for V pi and equation for VO. We can actually express the two-port C mu network as a Thevenin equivalent model. Okay, so this branch is caused by this equation, V pi equal I V pi, okay, which is this, the input source, equal to I1 multiplied by 1 over j omega C mu, which is the section, plus the independent voltage of VO. Okay, then this section here you have VO equal I2 over 1 j over j omega C mu, which is this, plus the dependent voltage V pi. So this is the Thevenin equivalent circuit. So from this Thevenin equivalent circuit, you can convert that to the Norton equivalent circuit. So you can have this. So technically, for the input part, you keep it the same, but for the output, you convert the voltage source, the voltage V pi. So basically, instead of a dependent voltage source coupled with capacitor, now you have a dependent current source coupling parallelly with your capacitor, and you can write this dependent current source, I call it ISC, equal to V pi over 1 j omega C mu. So after deriving the Norton equivalent model for the two-port C mu network, like this, you can now do the next step of replacing the C mu two-port network, which is this in here, with the equivalent circuit that you derived previously. Okay, so now you have this small signal equivalent circuit, including the two-port equivalent model of the capacitor C mu. So there's a couple of questions we need to answer in here. So the first question is, let's say we need to find at which frequency that these two dependent source will be equal to each other. Okay, because I want to compare these two independent sources first. So I want to see if they equal to each other, what frequency will make that happen. So first I can assume that the magnitude of this current equal to the magnitude of this current. So I have this equation here. Okay, this magnitude is basically omega C mu multiplied by V pi. Okay, I can write omega as 2 pi f easily. Then I can move everything else except for f over to this side. The V pi cancel out and I have this equation. Now I will use some typical value of Gm equal 50 milliampere over volt and C mu equal 0.05 picofarad. Plug in the number. I can have the frequency that make these two dependent current sources equal to each other will be 159 gigahertz. Okay, you will probably never going to operate your BJT anywhere close to this high frequency. Therefore, you can assume that ISC, which is this dependent current source, will never come close to GMV pi, which is this dependent current source. So question 2, I want to see at which frequency that the magnitude of this impedance, the impedance of C mu, will be equal to the impedance or the resistance of these two parallel resistors, RC and RL. So in order to do that, I have the impedance of C mu, I write that in the terms of frequency, so 2 pi f, 1 over 2 pi f C mu, equal to the parallel 2 here. So now I can write this as a function of f like this. So if I assume nothing crazy here, just typical number CR equals CL equal 4 kilo ohm, I can have f equal 1.59 gigahertz. So okay, so with 1.59 gigahertz, there's a chance that you may come close to this. However, oftenly, the operational frequency of BJT is very much more smaller than 1.59 gigahertz. If so, you can assume that the magnitude of the impedance of C mu will be much larger, okay, than RC over RC parallel RL. Why? Because okay, if this one come very small, then because it's in the denominator, this fraction become very large. Okay, so this one will be a lot larger than this. Therefore, you can consider C mu as open circuit. What are the conclusions that we learned from the previous slide? So for typical operational frequency for BJT, there are two things that we can assume or estimate in here. First of all, since this dependent current source ISC is a lot smaller than GMV pi, therefore we can consider that ISC is negligible. Therefore, we can remove this dependent current source. The second thing that we learn is for typical operational frequency, C mu can be considered as open circuit. Therefore, we can remove this C mu in here. So now our equivalent model is further simplified to this. So after all of those hard work, we have a further simplified equivalent model. So if you consider between the dotted line here, okay, what you can see is now you can relate this current and the voltage across this whole thing here, or easily you can consider this current and the voltage across this capacitor. So the voltage across this capacitor, or the impedance of this capacitor, is V pi minus VO. If you divide that number for 1 over j omega C mu, which is the impedance of C mu, okay, according to Ohm's law, you can have this equation. Now you factor out j omega C mu, you can have j omega C mu multiply V pi minus VO. Okay, so this is your first equation expressing the current I1. Now if you consider the output node, so you can use the same thing. Okay, so the voltage across this parallel resistor is the current going in multiplied by the total resistance. So the current going in is negative because it's different direction. So negative GMV pi multiplied for RC parallel RL. So now if you plug in this equation back into this equation, so you replace VO with negative GMV pi RC parallel RL, you can have this equation here after all of the magical arrangement. So take a minute to look at this equation. So in this equation here, you have a current term, right? So you have a current equal to an impedance multiply, you have a current equal to a voltage divided by an impedance terms. So if you consider this whole thing here is another new capacitor, and I'm going to call this Cm. Right? So j omega Cm or 1 over j omega Cm can be your new impedance. So effectively I can replace this whole thing to be one single capacitor Cm. So now I have only one capacitor Cm, and this Cm here is called the Mueller capacitance, and the multiplication effect on C mu is called the Mueller effect. So let's go through one example together. So for the previous circuit, if I give you RC equal to RL equal to 4 k ohms, R pi equal to 2.6 k ohms, RB equal to 200 k ohms, C pi equal to 0.8 picofarad, and the internal C mu equal to 0.05 picofarad, with GM equal to 38.5 milliampere over volt. Okay, so I want you to find the 3 dB frequency or the corner frequency of the current gain, assuming both with the Mueller effect and without the Mueller effect. So first step, we have to find the current gain. So when we find the current gain, we have to take the output first. So the output is pretty simple here. The output equal to the current going into the load resistor RL. Okay. Therefore, you can use the current divider law. Okay. So the current going in here multiply for RC over the sum of RC and RL. So remember, it's a little bit different from voltage divider. So for the input, you can consider this loop. So you have V pi, okay. So the current going through is equal to V pi over the total impedance of RB parallel R pi, parallel impedance of C pi, and parallel impedance of Cm. Okay, now if you extract all of this out, you can have it will be equal to V pi multiplied by 1 plus j omega of B parallel R pi, then multiply for C pi plus Cm, because two parallel capacitor, you can add them together, then over RB parallel R pi. So now you have the input, expression for input related to V pi, expression for output related to V pi. You can divide one for another and cancel out V pi. That's how you have these terms in here. So next step is to find the corner frequency. So if I call this whole group, to be tau 0, which this is the time constant. Okay, if this is the time constant of our circuit, we can calculate the 3 dB frequency or the corner frequency from the time constant by the equation of the corner frequency equal 1 over 2 pi time constant. Then you plug in the value for time constant. Okay, now there are two scenarios. Without the Mueller effect, then we can assume C mu equals 0. Therefore, Cm will be equal to 0. So you cancel this Cm terms out. You plug in all of the number, then you will have the answer of 3dP frequency to be 77 megahertz. Now, with the Mueller effect, you can have Cm to be equal to C mu multiplied by 1 plus Gm parallel with Rc parallel Rl, as we discussed before, and that Mueller capacitance will be 3.9 picofarad. Therefore, the 3dP frequency now is a lot less, and it is 13.2 megahertz. So it's a lot less than 70.5 megahertz when you take in Mueller effect into account. If someone asks you what is the Mueller effect in this circuit, you can basically use this factor 1 plus Gm Rc parallel Rl. If you calculate this number, that will come out to be around 78, and that will be your Mueller effect. And the Mueller capacitance in this case is approximately 5 times larger than C pi, right? So this means that the actual transistor bandwidth is approximately 6 times less than the bandwidth expected if the Mueller effect is neglected. Okay, so this is the last slide of the lecture today. Excited, huh? So in the left figure, you can see that this is the half pi equivalent circuit of BJT, where the load resistor for this circuit at the output is RC. While in the right figure is basically the equivalent circuit with the Mueller capacitance. At first approximation, we can see that the output voltage is going to be negative GmV pi RC. So if we assume that the signal is sinusoidal, so V pi is sinusoidal, we can plot our VO to be also sinusoidal. And if you look at the sinusoidal signal in there, you can see that the peak, the maximum of V pi is a lot smaller than the peak, the maximum magnitude of VC. So you can see in here, the distance between here and here is smaller than from here to here. Also, another thing is, so this sinusoidal is curving up, then down, right? Why this sinusoidal is going down, then up. In order work, you can say that there is a 180-degree phase shift between these two signals. Therefore, so due to the difference between the voltage, we can have the conclusion that Cm, which is the Mueller capacitance, is a lot smaller than C mu. A lot larger than C mu. And because of the phase 180-degree phase shift in the voltage gain, the voltage across C mu is quite large, and leading to a relatively significant value of capacitor current in our current IC, the current coming into CA. So in order to have the current in the Mueller capacitor Cm to be the same with the smaller voltage across Cm, the value of Cm must be relatively large, and this is the physical origin why we have the Mueller effect when Cm have to be a lot larger than C mu. So I believe I finished catching up with last week's material. So for this week, let's slow down a little bit. I believe you all have enough material to cover for your lab. So for this week, let's have only 2 or 3 more lectures. So I'll see you guys next.
So just to sum up, as you can see, when we start adding more realistic thing like parasitic element or internal capacitor like C-mu or Mueller effect, things get a little bit more different, 6 times different in corner frequency or 6 times different in bandwidth. That's a lot. So therefore, as an engineer, when you start with your model, you want to start with something very simple first so that you can understand. But as you go, you want to start adding more and more realistic effect so that you can have a more correct model to design your circuit and to predict the behavior of your circuit. So that's it for today, and now we see you guys next time.